Hello to everybody. Today we are going to proceed where we ended the last lecture. So until now we have been dealing with let's say problems which usually consisted of only one loop, and then we had to somehow just let's say realize those problems in a way of state machine. And so in that way we just had to prepare let's say an algorithm how to solve the problem, and all those solutions consisted of only one loop, but in general it's not a very good practice just to consider solutions in that way. So I will give you an example. So, for example, we had earlier a problem where we had to take care of what happens to the user interface, and if there is a change in some control in user interface, we have to acknowledge that change, and afterwards the change has been acknowledged. We go through the states which we defined before. But what, for example, the algorithm how to solve or to program that solution was the following. So we would enter a wait state, and in wait state we would wait for the response from the user interface. So if some of the buttons have been clicked or something like that. And so if one button is clicked, for example, it triggers a series of let's say events, which are not really events, but a series of states we have to go through to solve that particular problem. And for example, if we have a wait state, we are waiting for press of some button in user interface, and then after that, for example, we are using a queued state machine. We are going to a number of states that are entered into queue. So let's say we have like 5 states, and let's say that in each of those 5 states we have to consider some timer, and that timer is, for example, in each state it lasts for 10 seconds or so. So in order to go back to the wait state, we have to wait for 50 seconds to go through each of the states that perform the solution to the problem. And in that way, this is not an easy task, because we press the button, we are going through each state, and what if somebody who is a user presses a button while we are in the states in any of the states that is not a wait state. So in a wait state we are having only a way how to handle user interface, not in any other state, you know. And in that way we are not capable of handling change in user interface if we are not in wait state. So in wait state something gets triggered, okay, we go through each of let's say 5 or 7 states and wait for 10 seconds in each state. Let's say in 30 seconds of that procedure somebody else changes the value of the button in the wait state, and we are not able to register that change. So we are not able to take care in parallel of the user interface and performing the work in all the states. So this is a general issue. So this can't be handled via using only one loop. So we have to consider at least 2 loops. Okay. Behind me I have an example how to handle that. Usually there are a number of, as you know, there are a number of design patterns that we use in LabVIEW, but one of the, let's say, most commonly used to solve problems of the type I mentioned just before is the producer-consumer architecture or producer-consumer design pattern. So I will go back to the block diagram in here. So there is an example how this really looks like, and what is here generally the issue. So we will compare this to the just regular queued state machine, let's say. So let me just find it. Okay. So this is a regular state machine with queues, with arguments. Arguments are not like of any important considerations right now in this context. But what you can see here, this part, you know, it is like initialization of entire program. So and afterwards, after we perform initialization in this context, we have to take care of making a queue, taking care of reference to queue, importing the first element in the queue, and so on and so on. Of course, resetting the timer, and furthermore, we have to take care of error signal, and we are doing that by using guard clause as usual. We are considering what happens if we want to stop the program, and furthermore, after going through guard clause, we have to take care of the states. So this this loop here, case loop, takes care of the states. So there is a one state, not so, let's say, important. This is an init state, that was the shutdown state, but just let's say regular states are like this. This is the wait state I've been telling you about, and what is the general idea here? So if we get a press in the user interface in front panel, let's say this is an example which shows how coffee machine works. So if somebody presses a button for cappuccino, yeah, which is on the user interface, we have to register that press. It is registered via event loop, and then after it's being registered, it enqueues all the states we have to pass through in order to make cappuccino. So it considers adding water, adding coffee, boiling, adding milk, boiling milk, mixing, releasing, and that's it. But for example, if in each of these states we have to consider some timer, and we have to be in those states for a particular amount of time. So I know for adding water it's 5, let's say, seconds. Adding coffee 5 seconds, boiling 5 seconds, adding milk 3 seconds, boiling milk 3 seconds, mixing 3 seconds. So when we leave the wait state, we will be out of wait state for 15 and let's say 24 seconds. And what? So, for example, after wait state, we are going to adding water, and we are here for 5 seconds, and so on and so on and so on. So. What really is the problem here? So we are 24 seconds out of these states, and then something happens, somebody else triggers a new user input. For example, he wants to make espresso coffee, regular espresso coffee, at the point of, let's say, time instance of 10 seconds, and then it won't be registered. The user interface would stall, okay? It won't be registered in this particular architecture. So the only way how it's going to be registered if we go back to the wait state and then trigger an event. Therefore, we have to think about different aspect, different way of providing a solution for this. So we get back to the previous example that was originally intended for you to be shown. So this is the regular example. It's not this example doesn't have so much states covered. It is just let's say example for you to understand the concept. So, and to explain what is the general difference between this and the previous example, and what is the general difference in a way how it handles all the possible aspects of treating either regular stopping of program, either stopping of program by providing some kind of error in each of these loops, so in the upper and the downer loop. Therefore, let's go into detail with this. So let me show first how it works. So it goes like this, for example. So in here it is provided just a simple simple way of dealing with some problem. So we have just one state which is, let's say, of some concern to us, which provides like reasonable work, and that is the following. So if we press Start Test button, it generates this pop-up window, and it says, okay, we are just showing that we are in case test 1. And if we acknowledge this one by pressing OK, we go back to waiting for another change in user interface. So if we press for test, it's the same, press for test, it just calls another pop-up window, and we just have to acknowledge that we've seen it in the user interface. And that is the only, let's say, reasonable thing that we have to consider here for, let's say, working with states. I will go in explaining it a bit more precisely with when I finish explaining the other things. What are the other, let's say, 3 cases that are considered here? So the one case is how we treat a general stop of this this particular program, how we treat if error shows up in the upper loop, and how we consider what, let's say, what happens if an error shows up in bottom loop. So, for example, I will go just by stopping this program. So when I stop this program, press the button stop, the program is stopped, obviously. We are here, we can see in shutdown state. So the state is shut down. And for now, it's okay. Let's go back to the mirror program. So in general, these architectures so provides parallel 2 parallel loops, which provides the following aspect of consideration of problem. So the upper loop is called producer loop, and it considers a way of handling a user interface in such way that it's always available for the program. So there is no way of happening the case like in the example before. So if we have, let's say, to be in 24 seconds out of the state where we take care of user input, the user interface won't stall, because this loop, this upper loop, provides that. So this upper loop is called producer loop, the lower loop is called consumer loop, and the entire architecture is, or design pattern is called producer-consumer design pattern. And this design pattern provides with the upper loop for us to have all the time to have user interface considered all the time. So if something happens in the user interface, it will be acknowledged, or let's say triggered by this loop. The other loop, the bottom loop, takes care of everything else. So takes care of the mere functionality. So if we go through many, we have to go through many states in order to perform the task, we will place this in the bottom loop. This is a simple example. Of course, it can be considered in much more, let's say, complicated case, when we have, like, for example, only one producer loop and many consumer loops. In that way, we are with producer loop handling, let's say, user interface, and with many consumer loops, we're handling different aspects of control or performing the task. Maybe let me give another example. So if we're using a producer loop, for example, taking care of acquiring some data, and we have to acquire that data continuously, and we consider, let's say, one consumer loop to process the data in some way. So we have to go through many states to process the data, then another loop to storage that data, so we can have, in that particular case, one producer loop and two consumer loops, and so on and so on and so on. The important thing here is that everything, as you can see, is done also with queues. And what is really important for you to remember, so the signals which are transferred by queues are transferred by reference. And in this particular case, you can see this, there is, let's say, a branch here. So from initialization of queue, obtaining queue, and placing the first initialization element in the queue, we have a branch over here, and it goes, one branch goes to the upper loop, to the producer loop, one branch goes to the lower loop, consumer loop. And afterwards, after dealing with those two loops here, we just have to implement what really is considered to be producer-consumer architecture. So this signal is by reference signal. So this queue has always the information about what happens in that signal. So if something shows up in the upper signal, it will be also referenced by an element in a down loop, which reference to the same queue. So both things that are, let's say, enqueued in each of these loops, either upper or lower, will be in the same queue, and the referenced, it can be referenced from each of these loops. On the contrary, error signal, the yellow one, is transferred via value, and in general we have to consider that in that case that we have to place here shift registers, and then if something happens, for example, if some warning shows up, we'll be able to catch that thing via that shift register, and to provide that warning can be, let's say, shown at the end of the work of the program. And furthermore, so this branching here provides, let's say, two values of errors. So this branch is separate, this branch is separate, and they are combined here into merge errors. And what really happens here? So how this helps us to monitor user interface all the time. So We said that that is the case of the upper. That is the task of the upper. So let us consider just the simple way of dealing with this. We already decided we have only one, let's say, reasonable state that performs some work that is not of consideration of either stopping button or provoking errors. So it is a start test case, and that case is working in the following way. So if there is a change of value of start test of its button in the user interface, we have to place into the queue that case. Of course, maybe it's not so clear here. We can, there is an input here to the input element of the enqueue function, and it says start test double dot test 1. It means that it is state start test, and test 1 is an argument of that test, and that parsing of these two things is provided with this function here. I will show you, and the delimiter 2 points says that okay, the first part of that is the state, and the second part of that is just an argument. I can show you this one. Okay, it is called parse state and arguments. You can see it's rather simple. So we have an input string, we have here, we have a delimiter, and we have the parsing between the parsing that delimiter provides. So the first part before delimiter, the second part after delimiter. The first part is the state, the second part is the argument, and we are using this function that is named match patterns. You can check how it really works. So it provides, it searches for a regular expression in string and provides that expression if it is in the string. And so one output is what is in the string before substring. Other one is the one that matches substring, and that matching substring is the one that is provided here as delimiter, like 2 dots. And there is a third output that provides string after the delimiter, so after the matching substring. And it's pretty simple. Okay, so let's get back to here. So what happens here? In this particular case, we are monitoring with this event structure here the user interface. We have, like, let's say, triggered change of start test button, and then the start test is just start test state is just placed into the queue. So as you know, it is first in first out queue. So this start test is placed at the end of the queue. Afterwards, so we are going to the guard clause. So take care here. Let's say general or the common practice is for the guard clause to be before the loop that takes care of either states or something else. But in this particular architecture, the guard clause is after the loop for handling the events. I will go later through why is that important and why is this difference taken into consideration here. So in this particular case, guard clause of course has two cases: if no error happens or if error happens. But let us consider the case if no error happens. So if no error happens, just these two references, reference for queue and for error will go to this no error case. Okay. And what happens down there? So if this start test is placed on the queue, and let's say we have been here already in the init state. Let's go here what happens in the init state, so we don't have an error here. We take the state from the queue, we parse that state, and if that state is init, we go to init, and init here is really simple. We have in here two indicators, and after, let's say before we start doing anything smart, we have to provide that those indicators are reset to default. So the only thing that we do here is reset those two indicators to default, and that is in state. And okay, so we got to the point that we have entered start test at the end of the queue, and next time this loop iterates the lower one, we have here the state, so the start test state. It's no error case. We pull the start test state from the queue. In here, that start test state is being parsed and taken, and it goes in here, okay, to the conditional terminal, so when the start test case is generated here at the input of this case structure, we are going to mirror case start test, and it simply triggers this pop-up window with OK button that will just show us in which state we are. I will show you how it works. So simply just run the program. So press the start test, it gets us to the start test case, pop-up window with this OK button is shown. We acknowledge this behavior, press OK, and then we are stuck in start test until something else happens. Okay, and then we stop the program. Further to analyze this behavior, we should go, for example, for producer error event. So this event is generated via simple button placed in front panel, so this button here, and in case this button is pressed, an error cluster named producer error cluster is defined, and that error cluster is defined in some way that it produces errors. So Boolean constant is true. Some things are defined here, so the code of the error, the source of the error, and here, okay, for the consumer error, of course, we will change these. For example, use this one. And what is happening over there? So this error is generated over here, and then it is driven to the event case, to this terminal, which provides us to enter the error state here in the guard close. This error cluster is placed in parallel with the main error signal. That is done because in this way this will be performed, this action. So maybe it will be more easier to explain it in this particular case. So when we enter this error state over here, it provides us with a shutdown state that will be enqueued at the beginning of the queue, and also what this case enables us is to stop this loop by placing this true constant here. One has to consider the trick here is that this error from here is placed in parallel with the main error, because the only time this in Q at opposite side function should run is the case when error signal is when the error signal exists. So if this was placed within the same error line as error signal, it would not execute this one. Okay, and that is it for this upper part. So the producer loop is stopped by here, and we have shutdown state at the beginning of the queue. So in here now we don't have the error, because this is the error from the lower loop. So we go in no error state. From here we pull the shutdown state, because it is the first state in the queue, and we go to the shutdown state here. Okay, in here what we have to take care of, so this true constant is moved to this conditional terminal, and the loop is being stopped. And so this concept here is not important for treating producer loop, as this loop is already stopped by this true constant, and this loop is already stopped by this constant, and so the generation of the value change of the stop button is not taken into consideration, and not important for this case. But what happens if we have a consumer error produced? Let's say we simulated it, once again really similar to the producer error in the upper loop, but you'll realize the concept. So why is this simulated originally in the upper loop? It is because we have to catch the event in the upper loop, because there is the only place where we have the event structure. So the consumer loop is error for the consumer loop is made by pressing a button on the user interface, and that value change of the button is acknowledged by this event structure. And what happens here? So we are just placing a state consumer error in the queue. Okay. So after all these events are taken into consideration, the consumer error is just placed here at the queue. Okay. Afterwards, that signal is moved here. Now, this is not a regular error, as you can see, just the way of placing this state in the queue. And then we go to the no error case, of course. Okay. In no error case, nothing really happens. So this loop is still valid. It's not closed. Okay. What is then happening here? So the consumer loop is put at the queue. Consumer error, sorry, is put in the queue, and when it comes to picking up that state from the queue, we are going in no error case, of course. And here we are taking that state from the queue. We are taking the element, we are parsing it here, and we have there a consumer error. So we have to go to that state, in consumer error state. What happens in the consumer error state? The real error is now generated here in this state. So this is once again the cluster. I'll show you. So it is like that. We change it to the source consumer error. We change the code, and there's an error. So state is X, and boolean is true. And in consumer error, we just move this error to the shift register. And in next iteration of the loop, in the bottom loop, we are acquiring that signal from here, okay? And we have that error signal over here. So we go into guard close. In error case, we then go to the shutdown. We enter the shutdown state here. And in shutdown, what happens? In shutdown happens the following. So true constant is moved to this terminal. It stops the bottom loop. And that now is the case when we are using this property value signaling, because this changes the value of the user control stop, and also it creates like a regular event. So in upper loop, a stop will be event stop will be considered, and what happens here that a true constant is moved to this terminal and the upper loop is stopped. This shutdown state is placed here, but it's not of importance right now because this bottom loop is already stopped. So in this way, both of these, let's say, loops are stopped, and it completes the program. Okay, I can show you what it really happens here with the user interface. And what is of importance here, just for you to remember, that this guard close here has to be placed in the right part of the while loop. Why? So let us consider the case if this is placed before. So if this is on the left and that one is on the right. So, for example, if we had like this, we had this case producer error here, and so event here with producer error here, and this guard closed here. What would happen in here? First, no error will be treated here. Then this will be treated. There is an error. Okay, that error will be placed to shift register. We will go there. Okay, and we will go to the error case and go to the shutdown. Okay, but then with new iteration, this waits for another event. Okay, we don't have timeout here defined, so this waits for another event. And we go here to shutdown state. Okay, shutdown is treated here, taken out of the queue, and in here it's happening what happens regularly, and that's it. But in that case, okay, we have to somehow check if this is before. We have to wait again for another event to be considered, and that is the reason why we place this on the right and not on the left, the main reason. So this is in general the design pattern that provide us with the possibility of taking care of user interface continuously for entire time of working with your application. Okay? Thanks.